fields and forces around and for conductors. So in this section, what they're talking about is you've got basically a wire and another wire, and they're adjacent to each other. And the question is, well, how do their magnetic fields interact? Okay. Well, let's talk about that. Over here, I've got a diagram of two wires, right? And you can kind of imagine that the wires are sort of coming, out of the page here, and the dot represents a current coming towards us, and the X represents a current going away from us. All right. So this is sort of like a three-dimensional kind of look. All right. Now, we got to remember, how do I determine the magnetic field around a single wire? Well, basically, you put your thumb and your right hand in the direction of the current. Okay, so there's the current. And so my thumb is going to wrap around, my thumb is going to point out towards the viewer, and my fingers will wrap around, almost like I'm grabbing a coffee cup sitting on the table with my thumb pointed up. And my fingers are pointed in the direction of the magnetic field. All right. Over here, with the current going towards us, basically the magnetic field is going around in this direction. All right. Like that. Okay. Now, that's a scenario where the two wires are going in opposite directions. The current in the two wires is going in opposite directions. Here, the current is going in the same direction. So I've got, let me make a better circle here. Let me make a better circle. There we go. And here as well. And as we know, we're grabbing a coffee cup here. And so my magnetic fields are in these directions here. Okay. So now let's zoom out and take a look at this. All right. Green is the magnetic fields. Notice the difference in these two scenarios. Let's talk about what's going on in the inner part. Notice here and here, both of the magnetic fields are pointed in the same direction, whereas here and here, they're pointed in the opposite directions. Okay, so let's talk about what ends up happening here. In this area, what we get is basically a bunch of magnetic fields that are all pointed up. In this area, we've got some magnetic fields that are pointed up and some magnetic fields that are pointed down. All right, field lines. Excuse me. Sorry about that. Like this and like this. And so, as a result, what we get are two different scenarios. Here, you get basically like this magnetic pressure, right? I don't think that's actually what it's called. So that you get like this overabundance of magnetic fields here. Okay. And out here, let's say I've got magnetic fields from this wire pointed down, okay, out here. And then this wire, it actually generates a magnetic field pointed up over here, though be it's very small. Okay. And then the same thing goes for over on this side, right? I've got some strong magnetic fields pointed down from the left wire and some weak magnetic fields pointed up from the right wire, right? So as a result, what we end up getting is a big magnetic field in the middle and some weaker magnetic fields on the edges out here. And as a result, based on this geometry, in this setup, these two wires experience a force, magnetic. They actually feel like they want to be repelled away from each other because of all of this magnetic pressure in here and sort of like this magnetic void out here. All right. These are not technical words, right? This is just my own interpretation of this. I'll also talk about a different interpretation of this, but this is how I look at it. Anyway, let's take a look at what's going on over here. Here I've got upward magnetic fields from the right wire, and the left wire also has upward magnetic fields, although they are weak. And then the same thing here. I've got downward magnetic fields from the left wire, and the right wire will produce, remember, it has big sweeping circles here, downward magnetic fields, though be it weak. And so basically I've got now a pressure here and a pressure here, and actually a void here, because these magnetic fields actually cancel each other out, right? And so as a result, you get a void in the middle and pressure on the edges. These wires actually experience a magnetic force that will push them towards each other. Okay? And so, in a way, the rule of thumb is if you've got opposite currents, then they will experience magnetic fields. Opposite currents will be pushed apart, whereas non-opposite currents, or currents going in the same direction, will be pulled together. They kind of want to join together. Okay. Anyway, so that's your idea here. The other way of interpreting this is just let's think about this guy's magnetic field. This is a second interpretation. This guy's magnetic field here. Basically, he generates an upward magnetic field here. Okay. So now let's use the right hand rules. So I'm taking my right hand, okay, and I'm pointing my fingers up, okay? I'm now currently pointing my fingers in that direction, up. So now, question is, I've got now this red current here, and it's a motion. It's motion of you can think of it as positive particles moving in the right direction. Okay, sorry, it's positive particles moving towards the board, inside, moving into the page. So now that means I point my thumb on my right hand into the page. So basically what I'm doing is my fingers are pointed up, my thumb is pointed in towards the page. Now, if you do that right now, you can see that the palm of your hand is pointed away, this way. And so basically what we've got here is we look at a magnetic field that's going up in this area. We've got a current that's going in. So this is your thumb is going in, your fingers are going up, and your palm is pointed out that way. And that's an explanation as to, that's how you can figure out that this works, because it follows the right hand rules, right? That's not an explanation. The explanation is more about sort of these pressures and voids here and things like that. Okay. Anyway, so that being said, let's do a few things here. All right. So the magnetic force on a conductor in a magnetic field is dependent on the current in that wire, and how much the length of the wire in the field, like how much of it is in the field. Is only just a short bit of the wire in the field, or is a long bit of the wire in the field? And it also depends on the magnitude of the magnetic field and the angle between the field and the wire, right? Or the current in the wire. And so you can figure it out. Oh, sorry, just moved it. You can figure it out using this formula. Current in the wire that's in the field, the length of the wire that's in the field, the strength of the field, and the angle between them, all right? And so, for an example, let me just say I've got a field here, and then I've got a wire that's going like this with a current in it, and the angle is going to be this angle here, okay? Right there. It's the angle between the field and the current itself. And you can actually use either one of these because the sine of both of those angles is the same. All right, so don't worry about that. And now, if we want to figure out the direction of the field here, I point my fingers in this direction. Fingers, all right? So I'm pointing down in that direction. My thumb would go in this direction here. All right. And now, if you're basically able to do that, you'd have to be quite a bit of a contortionist, or you'd have to move the paper around a little bit. Note I'm rotating. Fingers, thumb. So it's kind of like my hand is like this. And my palm is not pointed up, but is pointed down, right? So I would actually get a magnetic force along this wire that would be pointed down, but not down in that direction. What I mean is down is like into the piece of paper, okay? So that's how that would work, all right? And there you go. Now the question is, well, how do I determine the strength of these magnetic fields? Well, we know these from the previous section. So basically, we could have a magnetic field generated by a wire or a magnetic field generated by a coil. So what ends up happening is these formulas here essentially get placed in that location, okay, based on whether or not you've got a wire next to another wire. So this is a wire next to another wire, or a wire inside of a coil or something like that, okay? So basically, if that's the case, you would see that the force magnetic is equal to length. Sorry, let me write that better. Is equal to the current in the wire times the length of the wire times the magnetic field by the other wire, which would be this, 2 pi r, times the sine of the angle, okay, between the wire and the field, all right? Wire and the field, okay? Not the wire and the other wire, okay? Now, as it turns out, if you're using the sine of the angle between the wire and the other wire, you actually use a cosine here, all right? If you're using wire as your angle, but you use sine if you're using wire field, okay? Because going back to this, notice that the field is going up, but the wire's going into the board, so that's 90-degree difference. Whereas over here we've got wire. They're both coming out of the board and into the board, so that's not a 90-degree. That's a 0 degrees or 180 degrees. Okay. Okay, now, over here, if you've got a wire inside of a coil, you would use Fm equals IL, right? This would be the current in the wire. This would be the length of the wire that's found inside the magnetic field in the coil. And then you would place your formula, mu naught, number of turns in the coil, the current in the coil, and then the length of the coil itself. That length right there is not dependent on how much of the wire, this wire, here, this wire is in the coil. And then, of course, you would put here the sign of the angle between the field and the field lines, right? The field lines and the wire itself. Okay. So here, let's do an example here. Two 35 gram parallel straight conductors, each 20 centimeters long, are 1 centimeter apart, with a current in opposite directions. What would be the current in each wire in order to have the magnetic force on each wire be twice that, the force of gravity? Okay. Oh, and this here part was supposed to be written down below. Actually, I was supposed to go electromagnetic induction. So I don't know why that's up there. But when I copied and pasted all this stuff, it got pretty messed up. I'll try and remember to move that a little later on. All right, so let me move that. Question is, I've got now 2 parallel wires. So I'm going to write those down like this. All right. And there's one, and there's the other. Okay. One above the other, let's say. I want their 35 grams. So the mass of the wire is 35 grams. Let's write that in kilograms. So 0.035. They're each 20 centimeters long. So I'm going to go with 0.2 meters. The distance between those 2 wires is R of, I'm going to go 0.01 meters. And they've got current in opposite directions. The question is what would be the needed current, right, in wire 1 and 2 in order such that it's twice that the force of gravity? Now, it doesn't really say, but I'm going to go with the assumption that I'm going to just run the same current down each wire there, okay? And so I'm going to say, basically, if I find one current, I've found them both, right? So the way that this is working, basically, I'm going to be using this formula up here, right here, because I've got one wire inside the magnetic field of another wire, okay? So I'm going to go ahead and write down that force. Force magnetic is current in one wire times the length of the field, right? The length of the wire that's found in the field times this mu naught, which, by the way, is mu naught, is 4 pi times 10 to the negative 7 or positive 7. I can't remember. It's negative or positive. I think it's negative. Anyway, we go ahead and write the current in the other wire there, and then we've got 2 pi r, and r is the distance between the wire and the magnetic field in question, okay? So the way that you think about this is you've got one wire that's creating a magnetic field that moves around it like this, right? It's like, think of like a magnetic field coming down, going here through that wire, right? And there, we've got ourselves a magnetic field. This guy's magnetic field is here, and basically this guy experiences a force based on the fact that it's in that magnetic field. So the R in question is the distance from this wire. So we're basically talking, it's the distance between the wires, which is this value here. And we want this to equal twice the force of gravity. Well, the force of gravity is just m times g, right? Well, it's twice that as well. And so there we have it. We've got our formula. We've got I squared, because I'm claiming that both of these are the same. Length of the wire, mu naught over 2 pi r equals mg, 2mg, right? If I want to go ahead and isolate for current, it's going to be 2mg. It's actually going to be 4mg because I'm going to multiply this 2 over. So I'm going to get a 4 mg over length of the wire, mu naught, and I'm going to root that. That's basically the current that goes in the wire there. All right. So yeah, go ahead and take a look at some of those extra example questions there, and shoot me some questions if you've got any on this stuff. All right.